See? Okay, so let's just remember what we've been learning. So last time we were together, we were going over a lot of definitions. I listened back to the lecture and I failed to mention something like critical at the beginning of it. So no one sort of asked, why are you telling us all of these things about the integers and the numbers and stuff like that? And you should have, right? And my answer in that case would have been, so we have to turn polynomials into a type of number system, right? So we have to study a number system that we're comfortable with, right? So we're all comfortable adding and multiplying and dividing integers. And we came up with terminologies like, oh, the integers are a group because they're closed under addition and have like an additive identity. Oh, the integers are also a ring because they're closed under multiplication and satisfy distribution. We also have that the integers are integral domain because they don't have any zero divisors. That is, non-zero elements can't multiply together to become zero. So what I want to do today is just continue through this, but with like the explicit sort of purpose in the back of our mind that we're going to have to repeat everything that we've done for integers for polynomials, right? Because I want the ring of polynomials with rational coefficients. I need it to be a group, I need it to be a ring, and I need it to be an integral domain in order to do anything interesting with it. So I think where we finished last time was at these addition tables. So we're talking about, I defined the remainder algorithm for you and the quotient algorithm. We talked about the properties it had. We talked about counting on a clock, right? Modular arithmetic. So on a clock, if we go from 1 to 12, 3 times 4 is 12, which is 0. So we have clock arithmetic on a clock with 12 hours is not an integral domain. We define this sort of notation. I'm going to say A is congruent to B mod C if and only if the remainder on dividing A by C is B, which is equivalent to this Julia command. We talked a bit about the symmetric mod. That is to say, if we're working mod 7, our canonical identifiers can be 0 through 6, or they can be -3 to +3. So we're going to switch between mod and the symmetric mod as needed. And then we started looking at very particular sets or groups, right? So we have this notation, Z sub 6, to denote the first 6 integers starting from 0. And we can generate its addition table. And I believe that's where we left off. So the way that we interpret this is that across the top here, so this is 0 plus 0. This is 0 plus 1, 0 plus 2, and so forth. Something like this is going to be 4 plus 3, which is 7, mod 6, which is going to be 1. What does it mean that there's zeros in here in every column? Every element has an additive inverse, and therefore this is a group, right? Effectively. We also have to notice that it's commutative because this table is equal to its transpose, right? That is, if you permute the rows and columns, it's equivalent. So let's now do multiplication. Can anyone tell me what this does? Oh, I should clear some of this input. Hold on. Where's the output clear? Okay. So we have this matrix. Whoops. So we have that matrix. What is this going to do? Yeah.
Returns a matrix of the same size where the entries are one if and only if they're 0 originally.
Sure. So what do we expect in the 0th position in this matrix? Or sorry, 1, 1. 1, yeah. So this is pointwise comparison or pointwise equality. It's saying put a true here or a 1 if and only if this cell is equal to 0, and a false or a 0 if and only if it is not equal to 0. So as long as there's a 1 in every column here, we can conclude that the addition table that we've given actually forms a group because it has these, every element is invertible. How can we find the additive inverse of a number? Well, we have to scan these columns, right? So suppose we want 0, 1, 2, 3. What's the inverse of 3? Well, we just have to find where this is 1, which is exactly what this does. And then go back here and tell it what row that it is. we do this, the inverse of 0 is 0, right? If we're adding, the inverse of 1 is 5. If we're adding mod 6, the inverse of 2 is 4, and so on and so forth. Would this be a good way? Is this like an efficient way of determining inverses in an addition table? No, I can't think of a worse way of determining the inverse for addition aside from looking at all of the numbers and asking. So this is going to be relevant. Let's look at multiplication now. So here's a multiplication table. So across the top, you see 0 times anything is 0. And on the first column, you see 0 times anything is 0. Actually, it depends how we do it. But in any case, 0 times something is 0 in both directions. 1 times 1, 2 times 1, 3 times 1, and so forth. What does it mean that there's a 0 here? There are 0 divisors in this set of numbers. So therefore, it's not an integral domain, which is going to be important. How can we make it an integral domain? Well, not this one. We have to change that 6 to something more appropriate, like a prime. If we made that a prime, then it would be every element would be invertible. So notice the multiplicative identity is 1, right? Because you have a column here which keeps all of the elements fixed, and same thing for the first, or I guess the second column, right? So the first row corresponds to 1, it doesn't change anything. The first column corresponds to 1, it doesn't change anything. And not all rows contain a 1, right? Which means not all elements here have an inverse. So since not all elements of this table have an inverse, what does this mean about its ability or inability to be a field? In a field, you should be a ring, but every element in your ring should be invertible. Am I muted? Can you hear me, chat? Yeah, okay, just ignore that. What's wrong?
It's just on the screen, it says you're using, but if you're using a different one.
Chat can hear me, so that's fine. And this is recording, or this is on. It's coming through, so I don't know. Let's just cross our fingers. Oh, I'll tell you what, I'll start doing a screen recording just in case. So we can have a backup. Okay, so I'm doing a screen recording as well. So we have a backup just in case everything goes to shit. Okay, so I have a multiplication table here. And if we look here, like 5 times 5 is 1, which means 5 has an inverse. But what is the inverse of 4 in this multiplication table? Doesn't have one. So it can't be a field, right? Because in a field, every element would have to be invertible. Let's look at this one. This is sort of interesting. 5 times 5 is 25. Mod 6 is 1, right? Because 6, 12, 18, 24, remainder 1. What's another way we can conceptualize this with the symmetric mod? Five would be -1 mod 6. So this is -1 squared, which is 1, right? So that's you can actually make some of the arithmetic easier if you move to the symmetric mod by exploiting some of the fact that it's smaller. Okay, so the multiplicative identity is 1. Not all rows contain a 1, which means there are some elements that do not have multiplicative inverse. For instance, there is no b in Z6 such that 2 times b is 1, right? So b is uninvertible. You can look at all of them. So what am I printing here? 2 times y. So yeah, we can show here explicitly that 2 doesn't have an inverse because we can just look at every element in the group, right? So 2 times 0 is 0, by 1 is 2, by 2 is 4, 0, right? So if there was an inverse, we would find it in here. We do have elements of this group which do have multiplicative inverse, right? If we go back to this group, we can see 1 has multiplicative inverse of itself and 5, but nothing else, right? So this is why we're not going to be interested in using rings that aren't fields, right? Because we do need things to be invertible. Okay, so let's look at a field. I said, if we restrict the number of integers we're using to a prime number of integers, then that's going to be a field. So let's just confirm this by looking at its multiplication table. Right, so I'm going to get all of the numbers 0 through 4, and then it's going to generate a multiplication table. So let's look at the properties of this table. Is it symmetric? Is it equal to its transpose? Yes, yeah. So that means that the multiplication operator is going to be commutative, which is something that we need. Does every element have an inverse? That is to say, if we look at every column, is there a 1 in every column that doesn't correspond to the 0 column? Okay, so like what is the inverse of 0, 1, 2, 3? 0, 1, 2. So 2 times 3 is 6, mod 5 is 1. Okay, so if I gave you a multiplication table for the ring that we were working with, we could read off a lot of these properties quite easily. So if you look at this now it's saying elements with a multiplicative inverse are every single non-zero element of that of those integers, and the only thing without a multiplicative inverse is 0, which will never have an inverse. So notice every column and row contains 1, aside from the first column, which corresponds to 0. For instance, the third column indicates that the inverse of 3 is 2, and correspondingly 3 times 2 is 1 mod 5. Okay, so we have groups, we have rings, we have fields, and I want to talk about greatest common divisor. So surely you've seen the GCD at some points, even if you didn't take number theory. So like, what's the GCD of 2 and 6? 2. Cool. Okay, so I'm just going to define the greatest common divisor for you. So the greatest common divisor is a super important operation of computer algebra systems. It's like one of the atomic operations. I found a serious bug in it once, and that was like a big feather in my cap for finding a mistake in something so fundamental. Here's how we can define it. And remember, we're working in constructional math. So I'm going to say, we're going to define a GCD to be something with this property. And then I'm going to assert that it exists and it's unique by giving you an algorithm. So first, let's look at the definition. So what is the GCD? So if you give me two integers, one of them has to be non-zero. We say that G in the integers is the greatest common divisor of A and B, and is denoted GCD of A and B. If you're from number theory, they don't even write the GCD. They just use rounded brackets for that operation. When? Okay, so these three properties have to hold. If G divides A, oh, are you guys familiar with this vertical bracket for divides? Okay, so if G divides A and G divides B, right? That is something that that is a property that the GCD has to have. It has to divide both of A and B. Number two says that if you have another integer and it divides A and it divides B, it also divides G. So this is just a fancy mathematical way of saying that G is the biggest divisor that you could find that divides both A and B. Because if there is another integer that divides both A and B and H and G, that would be bigger than G. And we need the G is positive just for uniqueness. Okay, so here's some examples, right? The GCD of 6 and 4, that's equal to the GCD of 2 times 3 and 2 times 2. And we can see, right, that the GCD of this is going to be 2, right? Because that's the most I can divide both by. Did you know that the GCD of anything in 0 is anything? That sort of makes sense, right? If you look at this, the factor 6 is 1 times 6. We can factor 0 in an infinite amount of ways. So I can say that this is 0 times 6. So it comes down to the fact that anything can divide 0, right? So what's the largest thing that can divide 6 and 0? Well, 6, right? So that's always going to be the case. The GCD of x and 0 is x, which is important because we need to write an algorithm, and that sounds like a great base case. So this is an inbuilt GCD function for integers. This is the one from like the Julia system proper. A lot of energy goes into these number theory operations like GCD. Surely they're not using the basic algorithm, but let's just run it while also recalling some Julia syntax. So what does this do? Okay, so like we can say, what does this do? Generate 5 random numbers in the uniform interval 1 through 100. That gives you a sequence of that. And then what does this do? Takes the product of all of them, right? So this is just going to give me a random number, which is guaranteed to be, is that true? This is going to give me a random number that is most likely going to be a composite number, unless somehow it randomly selected 1 5 times. I guess that's the one degenerate case. If I did this, I think now I can say these are properly going to generate composite numbers. So let's just do that. Right, so we very quickly determined that the GCD of this number and this number is 6,200. Right? But again, lots of energy goes into this. Generally speaking, how is the GCD computed? Have you ever been taught how to compute the GCD? Or yeah, I know that's why I don't like using Jupyter notebooks, because it spoils the story. Okay, so have you encountered Euclid's algorithm though? Okay, so what happens if I have an integral domain that also has Euclid's algorithm in it? What's that called? Huh? Euclidean domain. Yeah. Oh, well, seems that you are familiar with some of these terms. Okay, so Euclid's algorithm is an extremely important algorithm, and this is what's going to give us the GCD of two integers. It's very close to the division algorithm. It's actually remarkably simple. I'm just going to give these three lemmas, and these three lemmas are sufficient for developing an algorithm for the GCD. So here are the lemmas. So if we have two integers that are strictly greater than 0, and we know that A is equal to B times Q plus R, and we can always generate Q and R using the quotient and remainder algorithm, with R strictly positive in between 0 and strictly less than B, then these properties hold. The GCD of B and A is equal to the GCD of A and B. Okay, that's no problem, right? We can permute the input. The GCD of A and B is equal to the GCD of R and B. So this is what happens when you take A and you divide out by B. You're left with R, and that's fine. The GCD of A and B is equal to the GCD of A minus B and B. These lemmas are actually pretty straightforward to prove. I'm sure if you take a number theory course, they ask you to prove them. But let's see how we can get an algorithm out of this. So what I'm going to do is just sort of combine rule 1 and rule 2 in this return statement, right? So when you write an algorithm, a recursive one, the only thing that matters is that your recursive call, so the thing at line 3, the input that goes there is smaller than the input that came into the function, which means that every time we recurse, we're recursing on smaller input. And then eventually that input hits the ground, and that's what our base case is going to be. So the base case actually is pretty simple. The GCD of anything in 0 is anything, right? So as soon as one of the inputs is 0, we can conclude. Okay, so that's what it says here at 2. Remember our fancy if statements, right? This says, if B is equal to 0, then go ahead and return A, right? This happens because of the short circuiting. Otherwise, call this algorithm again, permute the input, which is allowed by lemma 1, and then the second position do A mod B, right? That is, find the remainder upon dividing A by B. And that's the Euclidean algorithm. Now, can we see that this is going to be less than A? You can't be bigger, right, than the thing that you're dividing out by, right? So even if you divide out by something larger than you, if you're like 4 and you divide it out by like 1,000, you're still 4. So this is that going to be smaller? Did I lie?
A is like 1 and B is.
Oh, right. Yeah. If A is smaller than B, then we're going to call and switch the input. And at the next step, B is going to be bigger than A, right? So that will push it down. And it doesn't take much work to show eventually that this is going to produce 0. Okay, so we'll hit the bottom. So it's just 2 lines to implement this Euclid's algorithm. I can show you that it's actually working. Right, so the GCD between 2 and 2 times 2 is 2. GCD between 3 and 2 times 3 is 3. GCD between 2 times 2 and 13 is 1. Right, but again, don't use it, right, the integer GCD algorithm, because it's going to be way more inefficient than like the inbuilt one. We wouldn't actually implement this recursively, right? Recursive algorithms aren't that great because they like need recursive stacks and create a lot of memory. But remember, in the back of our minds, we're thinking all of this stuff is going to have to be done with polynomials. So like, is there anything here that will prevent us from using this exact same technique for polynomials?
We don't have the remaining.
Yet, right? But if I can get a remainder algorithm for polynomials, we're going to get the Euclidean algorithm, correct? And you guys have done some synthetic division in high school, surely? Something that looks like this, which we're going to go over in a bit. Yeah, yeah. When you have to integrate stuff. Okay, let's keep going. Okay, so there's something called the extended Euclidean algorithm, which is a little bit more useful than Euclidean algorithm, because what we can actually do is, given A and B, generate a linear combination that's equal to their GCD. And this is a little bit more useful. And this S and T coefficients are called Bezout coefficients. If you remember what I was talking about last week, when I said, oh, here's my contribution to science is adding these numbers in front of these sets, those were also Bezout coefficients, right? So in this case, we have to think that they're going to help us determine multiplicity. But what these Bezout coefficients are going to allow us to do in this instance is generate inverses quick, right? Because the only way we have to find the inverse of an integer like mod 7 at the moment is just to look at all of the numbers between 0 and 7 and do the multiplication. That's the work. We can't have a linearly expensive multiplication algorithm, right? Multiplication is something really that has to be constant. Okay, so if we extend the algorithm to generate these Bezout coefficients, which we can do with the following changes to the usual Euclidean algorithm, it's not overly important that you understand. Let's just do this. Right, so we have 4 and 12 here. And if we call this extended Euclidean algorithm or integer extended Euclidean algorithm, we're going to get the Bezout coefficients 4 and 12, right? Because 4 times 1 plus 12 times 0 is equal to 4, which is equal to the GCD of 4 and 12. So here's our linear combination of 4 and 12 equal to the GCD. 9 and 12, their GCD is going to be 3, which is 9 times minus 1 plus 12 times 1. Right, so there's our linear combination equal to the GCD. And this is the important one. The GCD of 4 and 13 is 1, and I can get a linear combination of 4 and 13 showing me that it's 1. Now, why am I interested in something like this? Yeah. You find an inverse. So look at this equation. And imagine taking the whole thing, mod 13. Well, I have this written down, but I might as well look at it. What happens to this term? 0. What happens to this? Well, it's 1 mod 13. What's this? 4 times minus 3 is congruent to 1 mod 13. So what does that tell us about 4? Its inverse is minus 3. What does that tell us about 9? Its inverse is 4. Yeah, 12 minus 3. Oh, no. Yeah, 12 minus 3. Did I do that wrong? What are we working in? Oh, 13. 10. Sorry, 10. Right? Minus 3 is 10 mod 13. Right? So if we run the integer extended Euclidean algorithm and get these Bezout coefficients, we get fast integer inversion mod rings of prime characteristic. So there's also an inbuilt integer GCD algorithm. And it sort of does the same thing. So don't use the ones that we define because they're super slow. Use the inbuilt ones. But I just want to show you that the original algorithm isn't that hard to understand. But the series of optimizations that they've put into it are extremely hard to understand. Okay, so here's all the GCDs that you have access to. So just don't use the one that we provided to you. So here's the extended Euclidean algorithm. I believe that's what that X is. So they're saying 6 times 12 minus 3 times 42 is congruent to 1, or is equal to 1 as a linear combination. This is saying 240 times 2 and 46 times minus 9 is equal to 47. Oh, but here they don't have uniquely defined Bezout coefficients. Okay, so this means that we get inversion in Zm. Right? Well, at least when m is a prime number. So notice the extended Euclidean algorithm computes inverses in the way that we just described. Right? So if we get this linear combination, so you give me a and b, a and m, and I know that a times s plus m times t is equal to the GCD of a and m. If we just take that equation mod m, this is going to become 0, and we're left with this statement. The GCD of a and m is congruent to a times s mod m. And if we want to find the inverse of A mod M, what does this need to be? 1. Okay, so what should we pick for M? Something co-prime to A, but why don't we pick something even more severe than that? Just make it a prime every time, right? So if we just assume here that we're modding out by M and M is a prime number, then what we're going to get is an equation like this, right? A times S is congruent to 1 mod M, and thus A inverse is congruent to S mod M, right? So extended Euclidean algorithm gives you fast integer inverses, right? Mod M. So let's just run this. To find the inverse of 5, mod 13, we're going to do this. I need to find the Bezier coefficients when I give the GCD algorithm 5 and 13. So that's going to be 1 and minus 5. That doesn't seem right. Let's look what did I screw up the order here? Oh no, the first position is G. Okay, yeah, sure. Okay, so 5, the GCD of 5 and 13 is 1. And this is the first Bezier coefficient that goes on 5, and this is the second one that goes on 13. So this means minus 5 times 5 plus 2 times 13 mod 13, or yeah, is equal to 1. So that's what I've wrote here. Oh, it should be this. 8. And then what has happened? Okay, so let's study this, right? So I want to find the inverse of 5 mod 13. So I find the GCD of 5 and 13. Well, I find the Bezier coefficients for 5 and 13, which in this case are minus 5 and 2. Then I need to find 2 mod 13. I'm confused. Someone help me. How did I screw this up? This should be quite easy. Okay, so I'm just going to do some writing here. So here, sorry guys, some of my son's daycare literally contracted scarlet fever, and I'm not feeling very well. I thought scarlet fever was something that we had eradicated, but apparently not. Okay, so we have 5, because I want to do this properly. So the GCD of 5 and 13, that's going to be 1. And it should be, we should have Bezier coefficients minus 5 times 5 plus 2 times 13. Oh, okay, yeah. Minus 25 plus 26 is equal to 1. Okay, then I want to take this whole thing mod 13, which makes this 0, which gives me this, okay, which implies 5 is, oh yeah, this implies that the 1/5 is congruent to minus 5 mod 13. All right, or another way of saying this is the inverse of 5 is minus 5 mod 13. And 13 minus 5 is 8. So that's why it's saying that that's 8. Okay, good. I haven't lost my mind yet. Okay, so you want to use this inverse mod function that we've provided, where you give it A and you give it M. And as long as M is prime, or bare minimum A and M need to be co-prime, then you're going to get an inverse. Chinese remainder theorem. So this piece of technology is quite important, because when I say integers, I mean integers. Like mathematically, I mean the integers. How many integers are there? More than we can ever store on a computer, right? So the computer is never going to be able to work with integers proper, right? We can simulate larger integers that don't fit into words by like allowing them access to like all of memory, but eventually you're going to fill up memory. The secondary problem is that if you have numbers that are bigger than like what the computer is used to computing with, that gets really slow. Okay, so what I want to do is come up with a strategy where I can do most of my computing using the machine built inbuilt integers, which are fast, and then at the end do one sort of recombination back into the proper integers, which can be slow. Right? So the benefit here of using this Chinese remainder theorem is that we're going to be picking these m's so that it makes the arithmetic that we're doing machine arithmetic, which is like pretty important. But if you just want to understand this from like a mathematical perspective, we can regard it as just making the problem easier, right? Like it's easier to solve a problem if you're doing it mod 2, right? There's like only 2 numbers in that group. And if it's possible to solve the problem in a bunch of smaller fields, then why not? Okay. So it'll help us solve things by hand, and it'll also make things way faster to do with a computer. So here's the statements of the Chinese remaindering, and I do, yeah, it does have the bound in here that you pointed out that it was missing, or I thought it did. Oh, problem statement. Yeah, this is not the theorem yet. So here's the problem. So I have a secret number. That secret number is designated u. You're allowed to ask me what the remainder of u is, mod anything that you want, and you need to reconstruct the secret number. So for example, if my secret number was 19, you would know that it's 4 mod 5 and 5 mod 7. And using that information, you can reconstruct the fact that u is equal to 19. And how are you going to do that? With an algorithm, right? I'm going to claim that the number exists and is unique and can be built. Sure why it did. So there is proof that the secret number is 19. So here is the theorem. So let capital M be the product of all of the little m's, right? Which are the things that you're dividing out by. Like we get to choose as many of them as we want. Practically speaking, these are just going to be a series of primes. There exists a unique integer on 0 through m minus 1, which is the bound that you wanted, such that u is congruent to ui mod mi, right? Such that this u is a solution to the problem that we want. Now, this isn't all of the integers either, but I can actually give you a bound that says, as long as your m is this big, the actual answer in the integers is inside of it, right? So as soon, like if I know that the actual answer is like 77 and your product of primes is like 80, then that's the answer both in mod 80 and in the integers, right? So I just need to give you a sufficient condition for how many of these primes you need to multiply together so that the answer you generate is an answer within the integers. Right? With the miracle that we're not actually computing with all of the integers. We're computing them always mod something, which is way faster. Here's proof of the existence. And this may be laughable, but this is why I kind of like the field of constructional math. So I'm saying that there is a number that satisfies that property, and it's this. It's that number. Now, that may be unsatisfying. So I'm just going to demonstrate to you that if you compute that number, that will give you the answer to the original question. So let's look. So let's study this, right? So u is equal to this number. That's what I'm stating is going to be the answer. So v1 is multiplied by nothing. v2 is multiplied by m1. v3 is multiplied by m1 and m2. vj is going to be multiplied by m1 through mj minus 1, all the way up to vk minus 1, right? Which is multiplied by all of them, right? So eventually you're going to have like, right? So here's the setup, right? The subscripts on u are the images. The subscripts on m are like the size of the residue class, and u is the original number. Okay. Notice the vanishing terms. If I take this and I reduce it mod mj, what's going to happen? Well, any term that has an mj in it is going to vanish, right? It's 0. So that means the only non-zero terms left are the ones from v1 through vj, right? So vj is the first term, is the last term without a mj. vj plus 1 will have it. That's why it went to 0. Does that make sense, right? So every time I take u and I mod it by one of these m's, right, you get a predictable number of non-zero terms. Okay. So what does that mean about u1? Okay, so if I take U and I mod out by M1, what's left? Just humor me. I know the answers are on the board, but it's funnier if we can have a back and forth. It's just V1. Well, V1 mod M1. So you think we can compute that? Yeah, that's just a remainder. Okay, but then what does this mean about U1? Oh, we have it now. And we know what U1 is, okay? Can I get, oh, sorry. That means I know what V1 is. U1 has always been known from the beginning, but now I get V1. I need to determine these V's, okay? Can I get V2? Okay, I don't know, let's see. What happens if I take this equation and I mod out by M2? Well, you're left with this, okay? But we know what V1 is. Do we know what U2 is? Yeah. Do we know what M1 and M2 are? Yeah. Well, that means that V2 is going to be equal to U2 minus V1 times the inverse of M1 mod M2. Can we do inverses mod M2? How? Extended Euclidean algorithm. Okay, so that because we have the extended Euclidean algorithm and we have the division algorithm, we have Chinese remainder theorem. And it's just as simple as, yeah, this is the answer here. Okay, so what you would do is basically just implement like this recurrence relation here, right, where you're just computing V1 and then that information is sufficient to compute V2 and so on and so forth. So that proves existence. You can prove uniqueness. It's not very difficult. You just presume that two different solutions exist and show that that's impossible, but we'll skip that. Okay, so here's a real example of doing the Chinese remainder theorem. So suppose that we know that U is 2 mod 3 and 1 mod 5 and 5 mod 7. What's U? Well, here are my UIs. Here are my M. I don't know why that doesn't have I either, but why not? Okay, so those are my M's. And then here is my solution vector V. And I'm just running through exactly what V's are doing. Right? I'm saying V1 is equal to UI at 1. V2 is equal to the difference of these times their inverse. And I'm also implementing, right, this. And if I run it, I'm claiming here that U is going to be equal to this number because by line 10, we're going to have values for V and we know M's. And let's just check if it's the case that the number that we calculated has the property that we state, right? That is to say that U mod 3 has to be 2, mod 5 has to be 1, and mod 7 has to be 5. Aha. But what number did we end up computing? Oh, 26. Sorry, I'm losing my mind. All right, so 26 is the magic number here, right? And 26 is 2 mod 3, 1 mod 5, and 5 mod 7. Right, so I think this is actually in your homework. I can't recall. What was there a CRT task this year? We had one last year. What are they asking you to do? I don't think there's anything to do on the integer one. I think you probably have to do this for multiplication on polynomials, if I recall properly. Okay. Okay, so there's an example there. Okay, where are we? Okay, so now we can start effectively. So we've been going through just the traditional number system, the integers, the one that you're used to. We learned that we can multiply and specifically we can divide them, which really means like we're finding remainders. We can generate inverses by using the extended Euclidean algorithm, which is an algorithm that gives us a linear combination of two numbers that is equal to their GCD. The integers, when they were restricted to a prime number of elements, are a group and a ring and a integral domain and a field. And now I want to do all of the stuff that we just did with integers on polynomials. Exactly the same thing, just extending all of those operations to the ring of polynomials. So what's the first thing that we need to check about polynomials? What's the first thing we talked about integers being? No, before that, a group. Okay, so let's just confirm that, or at least discuss it so that it seems plausible that the coefficient polynomial ring forms a group. Okay, so first some notation and terminology, most of which you should be familiar with. So a polynomial is something like x squared plus 2x plus 1, but not like x squared plus 1 over x minus 1. This is called a rational polynomial. And it's also not something like x sine x, because sine x is it's in a larger category than that. Special functions, right? Things, well, it's basically things that you have to look up in a table to integrate, right? You have to be told explicitly what the integral of sine x is, right? There's a whole category of stuff like this, like the special factorial function. I forget what that's called, but there's a whole category of special functions. The point is they're not polynomials. Like polynomials are things that look like this. So if R is a ring and A is in Rx, we're going to denote a polynomial in this ring to be this. Okay, so I can say A is a polynomial with coefficients from R and whose indeterminates are from X, right? We can have, polynomials can have more than one unknown, but we're going to restrict ourselves to univariate polynomials. Well, each of these individual summons are called terms. This is called the leading term because it's the one with the largest degree. This is called the unknown. This is called the degree. And this is called the coefficient, right? And in particular, this one's the leading coefficient. But like all of this terminology should be known to you. Yes? Okay, cool. Okay, because it's important. So what's the degree of like a constant? 0. What's the degree of 0? Like how many ways can we represent 0 in this ring? 1, because I have this here. If I took that away, then it would be an infinite number of ways that we can represent it. In fact, we don't need that. Like nothing's really troubling mathematically to have 0 plus 0 plus 0 plus x squared. Like we're not really troubled by that, but we are troubled by that if you're implementing this into a computer. So strictly speaking, we don't represent terms that are 0 that are larger than the degree of the polynomial itself. But since 0 is so sort of weird, the leading coefficient, its leading term, they're equal to 0, but we actually designate the degree of the 0 polynomial to be minus infinity. That just, I don't know, this helps deal with some strange edge cases. So if this ever comes up, you should know. This is how we're representing polynomials in the Julia project. Right? So I said a polynomial is a sum of terms. So the first thing that we want to do is like to define what a term is. Right? So this is what a term is. A term has a coefficient and a degree, as we discussed. If we can't instantiate terms that have degree less than 0, like that's not a polynomial, the exponents here have to be positive integers. And we have to be careful about zeros, right? If you give me a coefficient that's 0, like what should 0x squared be instantiated as? The 0 polynomial, right? I said this a couple weeks ago, or maybe last week. Zeros are going to be a huge problem, right? Because we have to designate 1 0 and make sure that that's the 0 we use every time when something should be 0. So this struct term is smart. It's only constructing legal terms, right? It would be impossible to generate like the 0 x squared term if you have to go through this constructor. So that's good design. It's like prohibiting the user from doing something illegal. Here's how you get the 0 term, and here's how you get the 1 term. Okay, so once we have a structure for holding or representing terms, the next thing that we want to do is arithmetic on terms. Now, I don't want to talk about this too much because why? How is it hard to like multiply a term by another term or add it? Well, yeah, let's start with multiplication. Is it hard to add? Is it hard to multiply 2 terms together? Why? And you produce another term, right? Multiplying 2 terms gives you a term. What happens when you add 2 terms? Depends, but you could get a polynomial. So multiplication is actually an easier place to start when talking about terms, because terms are closed on multiplication, but not addition. Right now, things are getting a little bit strange. But here's the struct for polynomials, right? The dense constructor, the one that you're going to have to change. This inner constructor is just basically saying how the zero is constructed. Yes.
Just have a question about this.
Which one?
About the polynomial.
Sure.
So what if we have, when we put in the VT, the vector terms, what if we have two terms of the same degree? Should that throw an error? Like right now, what it's doing is.
Oh, this will be answered in a second. Because I agree that that's degenerate, but we're never going to allow users to create a polynomial like that. If that makes sense. Okay, so I'll go back to this. I'll just, okay, so you see how we did this? No one's going to instantiate a polynomial with your system by typing polynomial vector term 1, term 2, term 3. That's a terrible interface. What we do is we're going to restrict our users. I have to run everything. Hold on. Let's try again. Give me a second. I have to go all the way to the beginning. Clearing output apparently clears everything. Oh, but I can do the same thing here. Okay. Insert below. So we have someone trying to attack us. We have this x, and I can say x is just the x polynomial. And we have z, which is 0. So we would always do something like this. That's how we instantiate a polynomial with this system. And actually, we can even screw with it a bit. Oh. Yeah, this isn't the fully, I shouldn't do minuses because that's something that actually has to be sorted by your system. Let me try. I think this would work. Is this broken?
No, squared minus x, which returns x.
Oh, sorry. I want to do this. Because this interface is going through addition, addition is cleansing all of this stuff. If I say add x and minus x, it just pops out 0. So the way that we're prohibiting the user for instantiating polynomials, it doesn't matter. You can just presume that no degenerate vector is coming in because we would never give it that. So this is a computer science terminology. Do you know what an abstraction barrier is? So the user knows that they can do something like this. They're sort of unaware that there's a polynomial structure underneath this. If they were aware and like tried to pass that something degenerate, in computer science, we call this breaking the abstraction barrier. It's like, you're not even supposed to know about this. Like you have to interface with us using this other way. That's the only way we guarantee that this works. In principle, yes. You could throw, yeah, I think an arrow would be appropriate. But you could also fix it by also doing additions, right? Rather than, it would be slower, but I take your point. Okay, let's go a little bit further. Okay, so we have these terms, and then the terms themselves, we've defined some arithmetic over, right? So it's really easy to multiply two terms together. We can even divide some of the terms, but adding is a little bit different. Okay, so here's the polynomial type. This just instructs Julia how to construct the 0 polynomial, right? That's create a new polynomial with a vector, which is just the 0 term. So that's what it calls when it does this down here. Okay. This is an attempt at cleaning. right? This one is taking out like filtering out all the zeros, right? So you can't say 0, 0, 0, 0, 0, 0, 0, right? We want the polynomial, because you could have made this empty. That was another option here. The zero polynomial could have been a polynomial with an absence of terms. We don't, I don't know, that creates a strange edge case. So here we said the zero polynomial is exactly the polynomial with 1 0 term. So this just prevents a situation where you pass this like 100 0 terms, right? Because then you could have, that's the situation where you have 0 is 0, and 0 is also 0 plus 0, and 0 plus 0 plus 0. This is how we can find the maximum degree, right? It's just a simple map. These are all the terms, right? So now that we've defined, what do we do here? Oh, first set all the terms with 0, that's fine. But this is the dense representation, right? This basically says that if there's a 0 term, like put it in, right? So this is a little bit, since we are going to have 0 terms in this, it's like a kind of mangled data structure. We would never do this, but in any case, like you're gonna be removing it, right? Because this one is explicitly holding 0 terms, and yours has to not hold 0 terms. Last year we did it with a heap. This year we're doing it with a linked list. It's effectively the same thing, right? Don't forget, you can look at solutions from last year, and it's going to be very similar to what you have to be doing. Okay. So, right, like we can create polynomials like this. Okay, so we've defined polynomials. We talked about how that they're a sum of terms. We have a term structure. We have a polynomial structure, which is not really a sum of terms, but like an ordered list of terms. Now we want to confirm that the polynomial ring is in fact a group. And in order to do that, I just have to tell you how to like add stuff together and demonstrate that it's inside the ring. So here's a dead simple way of adding stuff together. Just need a little bit more width. That's now too small. Okay, hold on. I'll just move the comment here. Huh? Okay. So this is pseudocode. It's not Julia code. It's not any code, but it's like what I hope is unambiguous enough for you to be able to take and implement into a system, right? So pseudocode is just how you describe an algorithm rather than implementing it. So in this case, this is describing the addition algorithm. If you give me A and B, polynomials with integer coefficients, I'm going to output A plus B, like by definition. So the only thing that we have to worry about in definition are these weird merging steps. So if so what we want to do with addition is the same thing that you would do if you're doing it on paper. You have two polynomials, and you're like asking what their leading terms are. If the one leading term has larger degree than the other, then it goes into the sum, and you move down one. If your two leading terms have like equivalent degree, right, like 2x squared plus 3x squared, that has to become 5x squared, right? So that's what this is doing, right? So you give me the polynomials a and b to add together. If they have the same degree, that means you have to combine their leading terms. And that's what this is doing, right? So the first term of the sum is going to be the addition of the leading terms. And notice, you may say, but how are you defining addition with addition? I'm defining polynomial addition with term addition. And we can define what term addition means, right? So we have to be careful with like where these operations actually live. If the degree of A is larger than the degree of B, then we just sort of take it out, right? If we do 3x squared plus 2x, the first term of the sum is 3x squared, right? That's what this designates. You just pull it out, and then you add the rest, right? We're deleting the leading term from A. We're deleting the leading term from A. We're deleting the leading term from B. And if the degree of B is greater than the degree of A, then it's just the leading term of B, and then you sum A and B minus its leading term. So is it the case that these are smaller, these inputs at the recursive calls? Yeah, at each recursive call, I'm removing a term, right? So they are getting smaller, right? By number of terms, which means eventually you're going to hit like a base case, right? Where both things are going to be 0, and then you'll have a negative infinity term. So be careful not to add a 0 term in this case. Okay, but what kind of interface, now that I've introduced this word, do we need our polynomials to have? Like, what do I continuously do here? Am I ever looking at like an arbitrary term of the polynomial? Do I index at all in here ever? No. So what are the only operations on the polynomial that I'm using? No, that's the term stuff. So what operations on polynomials are being invoked here? Well, what functions are invoking on A or B? Degree, leading term. And if you have the leading term, do you have the degree? Really, all we need is leading term. Okay, so you need a polynomial structure that can give me its leading term really quickly and can delete its leading term really quickly. This is why last year we recommended a heap structure, because it's literally the ideal type of data structure for doing this. Instead, these are giving you like an ordered linked list, right? Because you want to get quick access to the leading term and you want to be able to remove it like really quickly. And if we did it in an array, we would have to do all of this shifting. Yeah.
Does that mean that we should store the linked list should go from this, like this?
I think that's why, I know this is why we added the dictionary into here, right? Because a linked list's property is that you get efficient deletion, but you get inefficient search. Dictionary actually is going to overcome that by just saying, oh, I'll just remember, I'll give you an index into the term immediately. Now, this isn't the best way to do it. In fact, I would never do it this way. But we can do it this way. It's like one possible way of doing it. So give it a go, right? And this really is the purpose of the project, is to pull out the current engine, right, of this polynomial and try a different one, right? Because that's really good design, right? Like the interface, like as long as you give me leading term faithfully and can remove it, I don't care how you stored anything, right? As long as those operations are faithful. So you guys have an assignment that's saying implement it like this. So just do it, right? And it may seem awkward, but it's because we can't give you the same question as we gave last year. Right now that this is the internet era, everything's just on GitHub. Yeah.
But if we just store it, because right now, I would imagine that people would store like the lowest coefficient, the lowest degree.
Yeah, I certainly wouldn't store it in ascending degree. There doesn't seem to be a point in doing ascending degree because you never need the tailing term. So I'll show you, we'll do multiplication next, and I'll show you multiplication only ever uses leading term as well, and only ever removes leading term. Right? Okay, so here's addition, and then here's addition actually implemented into Julia, like using that pseudocode above. Here's the term arithmetic when it's mixed, right? So I have to tell, so this will define what it means to add a polynomial and a term, right? One term at a time. But I also need to say how to add a polynomial and an integer and a polynomial, right? Because technically the constant term, I want to be able to say x plus 1 instead of saying x plus x to the 0 times 1, right? So this is just an edge case provision for the constant tailing terms. So how can we add one polynomial and one term, right? So I have A, I have the leading term of B, and I want to put it in P. How can I do that? Yeah. Yeah. Yeah, perfect. So effectively what we need to do here is figure out where it fits. Where does this fit? Right, you have a polynomial. I want to insert a term into it. So there's either a term with the same degree, in which case I have a merge, or there isn't, in which case I just have to like insert this into the list somewhere. So that's what so this is using last year's push and pop. But I believe you have the same interface into your linked list. There's no reason you can't get a push and pop from your linked list. So this implements using heap, but again, I don't care. Like as long as your push goes into your polynomial and gives me the leading term and removes it. Doesn't really matter. Okay, so I'm going to copy P, and it has to be a deep copy because you have to copy the terms as well. If the degree of T, the term I want to add, is bigger than the degree of P, that's easy, right? It becomes the first term of the polynomial, the new sum of the polynomials. Otherwise, you just sort of have to go through and scan to try to find it, right? And so this is what this is doing. If you let me see, where is it that we find? Yeah, here's where we find it, in which case we're just increasing the coefficient of that term by T. And this is where we don't find it and where we're doing an insert. So here we're using indexing because this is a vector. You're not going to have that for your polynomial. And then this just is an edge case provision to remove zeros that may have gotten introduced, because technically speaking, this could have produced a zero term, which we shouldn't have put into the system to begin with. Okay, so let's see. So that's adding one function, that's adding one polynomial to a term. So if I can do polynomial plus term, how do I then do polynomial plus polynomial? Well, that's easy, right? So a polynomial is just a sum of terms. So just if I want to add P1 to P2, that's just the same thing as adding every term of P2 to P1. And we've already defined what it means to define a term to a polynomial. So you just do this successively, okay? Is there an addition task for you guys? Yeah, you have to change. Well, you just have to make sure, because the addition that we implemented is presuming a different internal structure of the polynomial. So you just have to make sure that it all works. The only difficult part here is just making sure you're not putting in zeros when you're not supposed to. That's the troubling part. Okay. So I'll just show you that we can add, right? So we have 2x squared plus 3x plus minus 5. And I think one of your tasks is to make it so that I can do minus 5 instead of plus minus 5. Here's another polynomial, minus 3x squared minus 4x plus 6. And their sum is going to be, so it's 2 minus 3 is minus 1, right? 3 minus 4 is minus 1. Minus 5 plus 6 is 1, right? So we faithfully produce the sum of those polynomials. Okay, multiplication. You may think that this would be more complicated, but it's sort of strange. Multiplying stuff in many ways is easier than adding stuff. And I can show you that this is the case for multiplication. So here's some pseudocode for multiplying polynomials. And remember, the only thing that I have to do is break multiplying two polynomials into a smaller problem and recurse. Okay, so recall distribution. This. Are each of these smaller multiplications than the whole multiplication? Yeah. Okay, so I can actually reduce the multiplying this to these 4 multiplications that are smaller. So imagine you give me A and you give me B. They're both polynomials. You cut them in half, right? And then you just you multiply them through distribution. And to resolve the actual products, you just do the same thing again. You call the multiplication algorithm again until what happens? You've only been past one term. And can we multiply 2 terms together? Easy. Okay, so all we did for multiplication here was recurse on multiplication with a smaller problem by just like being clever with the distribution. Now there's a bunch of other constraints that I put here, and it's basically like prohibiting people from breaking up polynomials in like really strange ways. Like you can't have 2x and break it into x plus x. Right? You really have to break it in such a way that at bare minimum, like you're not the degree. If you break the polynomial in half, one of your halves has to have larger degree. Right, that will guarantee this, and you can't do things like say, like add something else that wasn't there. And I can't say, oh, now you have an x cubed term because I put a minus x cubed thing in the other one. So given 2 polynomials and split in half without any funny business, you can do this, right? And what I highlighted here was prohibiting funny business effectively. Okay, so then how do we implement this into Julia? Well, again, I want to define how to multiply 2 polynomials together, which means I also have to define what it means to multiply a polynomial by a term, or a term by a polynomial. So that's what these 2 things here say. So it basically just promotes one of the terms into a polynomial and then and then calls the multiplication algorithm. So here's really the meat. And you can see it's easier than addition. Like, who would have expected that multiplication is going to be easier than addition? But all we're doing is what I just talked about, right? Doing a smaller multiplication, but we're cutting up the polynomials in like really, in not the best way. I'm breaking it up so that b gets broken up into its leading term and the rest of it. Right, so you know how you would do if you were to multiply two polynomials together, how would you do it? You would like take the leading term of the first and multiply it against the entire second polynomial. Then you'd move to the second term and do it again, the third term and do it again, and then you'd sum up all of those things. So that's all this is doing. I'm saying for every term in polynomial 1, my answer is equal to answer plus t times the second polynomial. This is just distributing every term of P1 over P2 and summing that, right? So it's quite easy. Now, this is the world's worst multiplication algorithm. There are way faster ways of doing this. And because this is how we implemented it in your homework, unfortunately, you're not going to like experience the speed ups that you're supposed to, right? Because we would have to give you the world's best division algorithm and multiplication algorithm in addition for you to really see some of these gains. But you can, like, interpolation is another fun way of multiplying polynomials. We discussed this last week. Because remember, 3 points on the plane uniquely identify a parabola. So if you have f and you have g, you just have to evaluate them a bunch of times and take their product and interpolate. That's faster than doing this, but like more complicated, obviously. Okay, so here we have some examples of the multiplication working. So I have P1 and P2, and you can multiply them, and there you go. Except this hasn't been prettied up yet, right? That x to the 0 shouldn't be here. Okay, so the following properties are consequences of our definition. Right, so why did I just do this? Well, I've defined addition on polynomials, and I've defined multiplication on polynomials, which means polynomials are a what? Ring, at least. Do we get 0 divisors? Well, we'll find out. Okay. So when R is an integral domain, right, when the coefficients for your polynomials don't have these 0 divisors, it'd be very weird to multiply two polynomials with non-zero coefficients and generate 0 coefficients. Then the following properties of polynomials exist, right? So the degree of A times B is the sum of the degrees. Is there a problem? Oh, leading coefficient, leading monomial, leading term. Sorry about that. Yeah, always ask. Because like a lot of this is like second nature to me, but it may not be for you. Okay. So if I multiply, I don't know what, I think that's not supposed to be there. But if you have, if you multiply A and B, what do we know about their leading coefficient of the product? Right? The leading coefficient of the product is going to be the product of the leading coefficients, right? The same thing about the leading monomial, right? The leading monomial of the product of two polynomials is equal to the product of the leading monomials, of course, polynomials. And the same is true about the leading terms. Yeah.
When you say the leading, is that just like x to the n?
Yeah, x to the n. So the monomial is the x to the n part. The coefficient is the thing you multiply it by, and the collection, like the product of those two things is called a term. Yeah. Right. Okay. So here, we just have to demonstrate that the product of two polynomials is in fact a polynomial, and you just do it by multiplying it out. Right. You say, okay, here you go. Right. If you give me two polynomials of finite degree, then I'll just take their product, and here it is. And does this have the same shape as is this in the collection of all polynomials with coefficients from R? Yeah. So then this is closed over multiplication. So it's a ring. The polynomial ring forms a ring. This is a fun thing to prove. We're going to need it. Every field is also an integral domain. There are no 0 divisors in fields except for 0, I guess. You should try proving that. It's a little bit fun. Okay, so one of your tasks is to level up the multiplication algorithm. Because if I give you two enormous polynomials to multiply by, that may overwhelm the computer. So what I'm saying is, hey, why don't we like look at the polynomial, but actually reduce all of its coefficients mod something. Like instead of using all of the integers for their coefficients, why don't you use like 7 of them, right? And then we can do the product like mod 2, mod 3, mod 5, mod 7, mod 11. And provided that the product of these primes exceeds some sufficient bound, then I actually have the product of the polynomials over the integers without ever having to compute with arbitrarily large integers, right? Which is a huge benefit here. So I need to define some, I want to extend Chinese remainder theorem to polynomials. So there's some terminology we're going to need for here. So here's a polynomial A. Its leading term is an xn. So it has degree n. And I want to define the height. Do you guys know what the height of a polynomial is? I can't see why you would need it. Maybe if you've done like Pythagorean theorem or the binomial expansions, the stuff becomes relevant. But it's just the largest coefficient that the A has, right? And you take the absolute values of them. So who cares about negatives, right? So 2x squared minus 5 has height 5. Are you guys familiar with these norms? Huh? This is the inf norm for polynomials, if you're familiar with that terminology. So cool. You guys know what norms are. They're important. Okay. We're also going to denote by number A, or I guess hash A, as Gen Z would call this, as the number of non-zero terms of A. So the number of non-zero terms of 2x squared minus 5 is 2. Right? How many non-zero terms can a polynomial of degree n have? N plus 1. Good. Okay. So if we intend to use the Chinese remainder theorem to calculate the product of two polynomials, and I'm not going to prove this, I'm just going to state it. Here's your sufficient condition for the product of the primes, right? You need the product of the primes to be greater than 2 times the height of the product, right? In order for us to say that the coefficients that you generated are the real ones, right? The ones over the entire integers. Okay, but this begs the question, how can I get the norm, or how can I get the, what was I calling it? Height of the product before I take the product? Any ideas? Well, who of you done analysis, real analysis? What's this? It's a bound, isn't it? Maybe if we can find a bound that's higher than this, that will be our sufficient. It doesn't have to be very sharp, but we just have to find something that's definitely in excess of this, and we'll use that as our bound. So we can do this. You can do a type of analysis, but you can try the proposition. This proposition isn't too difficult to prove. It's just really arithmetically messy, right? So here's a proposition. If you have the product of two polynomials, if you take their product, the height of the product is less than or equal to the height of A times the height of B times the minimum number of non-zero terms of either of them. Right? And we don't want to put max here because we do want to keep these things sharp. And you can prove this just by doing a worst case analysis when you multiply A by B. Right? So just look at A and then replace all of its coefficients with its height. Just say that every coefficient is alpha, which was the biggest one that we could find. And then say B, every coefficient is beta, which was the biggest coefficient that we could find. And then multiply those two things together. And after doing some combinatorics, you will produce this result. Right? So proof by magic, I guess. Right? So you analysts enjoy this type of self-pain. So you can play with some of these boundaries. I was never much of a real analysis guy. Okay, so how do we then use this to do multiplication? So here's a real example. Okay, so I have A, B, and C. So C is hidden, right? We don't actually know that this is the product yet. I'm just writing it down for us because this is a tiny example. The height of C is what? 20? The height of A is 4. The height of B is 6. The minimum non-zero number of terms in either is 2. So I know that the height of C is no bigger than 48, which means in our Chinese remainder theorem, strategy that the product of primes has to be greater than 48 in order for us to say that the result of Chinese remainder theorem is actually giving us the result over the integers writ large, right? Not just a finitely many of them. Okay, so A is 3x minus 4, B is 6x plus 5. Their product is 18x squared minus 9x minus 20. So let's look at these products, but limit the coefficient field to mod 5, mod 7, and mod 3. So here it is mod 5, right? 3 mod 5 is 3, minus 4 mod 5 is 1. That's how we get this one. 6 mod 5 is 1, 5 mod 5 is 0, right? So the first one, we have to do 3x plus 1 times x, right? So that gives us 3x squared plus 1x plus 0. That's the product mod 5. Yes, sir. I'm not modding out by the coefficient. I'm not taking a remainder mod 5 because I think that always produces back f. When I say mod 5, I'm saying the coefficients are now restricted to Z5. They're no longer from Z, right? They're from Z5. The coefficients are from that ring, right? It is. Yeah, we'll talk because I haven't even defined remainder yet. So that would just be like doing x minus 1 divided by 5, which is like 1/5 x minus a fifth. That doesn't, right? We'll get to it when we get to it. Okay, so in any case, here are, but maybe I should clarify that. When I said mod 5, I'm saying we're restricting the coefficients to Z5, right? Not the whole integers. So mod 7, 3 is 3 mod 7 minus 4 is 3 mod 7. 6 is 6 mod 7, 5 is 5 mod 7, and this is their product. Mod 3, you get 0x plus 2, 0x plus 2, 0x squared plus 0x plus 1. This is super easy to do the product mod 3 because everything sort of disappears. Okay, so ignore the fact that we know the answer. How can I then get the product from this? What's 3 times 7 times 5? Is that bigger than 48? Well, 7 by 5 is 35, right? So twice that is 70, and we're doing 3 times that. So it's certainly greater than 48. What should I do here to recover this answer? Oh, this answer. Okay, so what does this look like? I'm saying I don't know the real product, but I do know that the product mod 5 has leading coefficient 3. The product mod 7 has leading coefficient 7, and the product mod 3 has leading coefficient 0. What does that sound like? The Chinese remainder theorem on integers. So I'm saying if you do Chinese remainder theorem on 340 with 573, you get 18. And if you do Chinese remainder theorem on 150 on 573, you get -9. Or in this case, you'd get the positive version of that, depending if you're using the symmetric mod or not. But you can always convert. So again, I know the constant term mod 5 is 0, the constant term mod 7 is 1, the constant term mod 3 is 1. By Chinese remainder theorem, it's -20. Right, so this is what you have to do in your homework. You sort of like implement this, but fear not, because I gave you pseudocode, which we're going to go over. So you just sort of have to like faithfully implement the pseudocode. But it's just this, like the idea is not too crazy, right? You just keep finding products, small primes, right? And then you recover their images using the Chinese remainder theorem, right? After selecting enough primes to exceed a threshold. Is there any questions regarding that? Yeah.
So if the height of the product satisfies under equality, then you can look at the Chinese remainder theorem for individual coefficients.
Yeah, and as long as you've done them for enough p's so that the product of p's exceeds that height requirement, then you're good for it to be the answer over the integers. You will see you'll get this polynomial back. And we're saying, oh, the answer is this mod 3 times 7 by 35, but it's also correct over the integers. Yeah.
And so you get only positive coefficients, right?
Yes. Yes.
That be taking finding the inverse of mod G1 times G2.
No inverse is required. You just have to subtract half the length of the modulo. So if you're working mod 7, just subtract 3 or 4. I may be off by 1. It's just a linear shift that you have to do, right? So it's easier than having to use inverses. So yeah, if this was smaller, I'd be able to do the mental arithmetic, but it's not. Yeah, I can't run it through Julia. Okay, but you shouldn't do it like this table. Because okay, the objective here is to make multiplication more efficient. So is this more efficient if I have to spin up like 1,000 copies of like my input polynomials and like let the memory explode and then shrink it? No, I don't. I think that's going to be worse than just sort of doing regular multiplication. So what we do instead is just like we do it one at a time. So we'll do Chinese remainder theorem on like 5 and 7 and have an answer mod 35. And then we'll get a mod 3 answer. And since 3 and 35 are co-prime, you can use Chinese remainder theorem then. So you're only ever doing one more product and updating the answer with Chinese remainder theorem. And again, there's some pseudocode for this. So let's just suppose we've defined Chinese remainder theorem where I can give it a set of u's. Remember, our u's are the images of the polynomials, mod P1, P2 through Pm. We're going to say that this is equal to u, which is a vector, such that UK mod, it's weird when it breaks up. U is congruent to UK mod PK. Right, so for example, from that chart, I was 3, 4, and 0. If I solve the integer Chinese remainder theorem for 5, 7, and 3, you get 18. That's what that was. Here you get 96. Okay, so let's see. Maybe I can do this. I just insert below. I want to know what 3 times 5 times 7 minus 96 is. Or did I do that backwards? I did it backwards. Minus 9. Yeah. Who is asking about negatives? Yeah, see, that was minus 9. Chinese remainder theorem told us it was 96. But if you do like the image minus 9, you get 96. So these are the same thing, right, on the clock. One just counts clockwise and the other one went anti-clockwise. Yeah.
How do we know that's a coefficient is positive or negative? How do we know?
No, that's a good question. What was my answer for that? Like well, let me get back to you on that one. It's a really good question. I know some like high level type of stuff, but it's probably not going to be meaningful. It's kind of like the answer is kind of like it doesn't arithmetically, it doesn't matter, right? Like these are equivalent numbers, right? But I guess since we move to like the whole thing, like we want negatives back. Let me put it up, ask that on the edge then, and I'll give you a more specific answer than that. I can't, but that's a really good question. So this is the symmetric mod conversion that you need. So you're just shifting by m half, right? If the number is beyond m, right? So if you want to know what 6 is mod 7, since 6 is beyond 3, you need to subtract. That would be positive. Okay, if I'm working mod 7 and I want to know what 3 is, you have to subtract 4 from that. So 3 would be minus 4, something like that. Sorry, scarlet fever. Don't make me do mental arithmetic. This is where I fail as a mathematician. This is why I get the computers to do it. Okay, so here they are here's the symmetric mod 7, right? So 0 is 0, 1 is 1, 2 is 2, 3 is 3. Now we're halfway beyond 7, like the middle of 7. So this is now why we get minuses, minus 3, minus 2, minus 1. And this is the way that you can convert them. But it won't become relevant until we need it to become relevant. So actually, if I run that CRT algorithm and I pop out the symmetric mod instead, now you're recovering exactly the coefficients that you require. I have another example here. That's fine. It's just I did another P for funsies. Okay. So here's the Chinese remainder theorem on 2 polynomials, like the like a pseudocode for doing this. That's still good. Okay, so here's how you multiply 2 polynomials using the Chinese remainder theorem technique. Right? Give me A, give me B. And these are polynomials that are over the, they're polynomials with integer coefficients, proper all of them, okay? And the output is going to be A times B in the polynomials with proper integer coefficients. And all of the intermediate calculations are going to be done mod P, right? Which is incredible. At the end, we're saying, oh, although I did only mod P calculations, I'm producing something that works over the entire integers. Okay, so we have to get the height of A, and we have to get the height of B, which isn't too hard. You just have to scan all of its coefficients and find the biggest one. Then you compute your bound, right, which is exactly the same bound that we worked out, 2 times the height of A times the height of B times the minimum number of non-zero elements in both. I don't actually count the non-zero elements here. What am I doing instead? Yeah, I'm just saying, I don't know. I don't want to count them. But if you're degree n, like you have n plus 1 non-zero terms at most. And since these are all inequalities, it's okay that I've put something bigger than necessary there, especially when it makes it easier to actually compute, right? So this is a little bit bigger than we need it to be. Then I pick the first prime, right? Then I have this m, which is going to keep getting bigger. We need m to be bigger than b before we can stop. And then you just do multiplication mod m, which is one of your tasks, right? You have to be able to have a polynomial, which is mod p, that can do, like when you do multiplication, its terms are getting reduced mod p in that process. And then you just run this loop, right? And this loop is just doing what I said. Instead of like generating all of the products, it's doing it, it's just updating it one at a time, right? So I'm saying, while the product of my primes is less than the boundary that I need it to be at, pick a new prime, right? So next prime is actually one of my favorite commands from Maple. Like this is saying, given P, I'm going to give you the next prime after P. That's a new one. Then I'm going to find the next image, right? So I'm going to do A times B mod that new prime. And then I'm going to call the Chinese remainder theorem, right? On the current product with its current M, and then the new product, which is mod P. And you're going to get back a new, you're going to get back a C, which is correct over M times P, mod M times P. And as soon as that is bigger than B, then you can return. Right, where this is just updating M. Any questions? Be honest, right? These conversations are good to have. Okay, so don't be tempted, because like the first time we did this, many people were like, I'm not going to do it the updating way because it's harder. I'm going to do it exactly like this table. And it didn't go well. Like it exploded their memory because you just can't do it that way, right? Because you may need a lot of these primes. Okay, so this is just something that you're going to have to implement, but you just have to faithfully implement this pseudocode. This is very close. How much time do I got left? Half hour? Okay, cool. Okay, so we have a polynomial ring, and we know that it's a group. We could add polynomials. We can multiply polynomials. Can we divide polynomials? We can divide some of them. So that's the same thing with the integers, right? Do the integers form a field? No. But do some of the integers divide them? Well, yeah. 4 divided by 2 is 2. That's still an integer. But 2 divided by 4 is a half, and that's not an integer. So this is relevant because this means that sometimes we are able to divide, right? Provided that we're in a situation like this. I can do x squared divided by 2x. Right? That gives me 1/2 x. That's closed over the polynomials. So even though x squared and 2x are from are polynomials, their division is in the rational. Even though that these are polynomials with integer coefficients, when I divide them, you generate rational coefficients. Right? This is because Z is in a field, but Q is. Okay, so what could we do? Well, I want to be able to work with fractions because I want to be able to do stuff like this. But that means we have to use fractions instead of using integers. And fractions are more computationally sophisticated than integers for a variety of reasons. Like for one, they have to be reduced occasionally. Right? If you keep multiplying and multiplying them together, like you have to do GCDs to pull out their they're common factors, right? You don't want to have like 4/8. You want to have 1/2. But what is true if we restrict the domain, like the coefficient field mod p? Can we have 1/2 mod 7? Yeah, we can, because that's the same thing as 1 times 2 inverse mod 7. What's the inverse of 2 mod 7? 2, 4, 6, 8. That's 1. Oh, yeah, 4. Right? 2 times 4 mod 7 is 1. Right? So 2 has an inverse of 4. Right? So we can still work with fractions as long as we regard the numerator as being a product of its inverse. Right? So instead of having 1/3, you have 1 times 3 inverse. And boom, we're working with fractions again. So it's not going to be a problem that we're going to generate rationals in our coefficients, because working mod p is going to sort that. It turns out that the ring of polynomials with coefficients from a field form a Euclidean domain. I'm not going to prove it, but this means that we get division and and extended Euclidean algorithm and GCD. We got all the fun stuff that we had on integers that we're going to need. So let's reconsider the division. Well, let's do this calculation now in Z7. Oh, geez, the example was right here. So I can do x squared divided by 2x mod 7. That's going to give us 4x mod 7. Right? So we're working mod 7, and we produce sort of divisions mod 7, which is fine. So here is the division algorithm for polynomials, okay, which is going to be the thing that equips us with remainder and quotient, which is the thing that we require to define GCD, which is going to be extremely important for doing the factorization algorithm, which we still haven't touched on, but I'll get there. Next lecture, we're going to do the meat. But this is almost identical to the integer division algorithm. We just have to have like a different notion of like what it means to get smaller. In this case, getting smaller means your degree is descending. Okay, so let's recall like what this meant from high school. Okay, so you like all of you are capable, or like were given a problem like this in high school, surely, or maybe here in calculus, right? To say 10x squared plus 4x plus 1, divide that by 5x minus 3. Now, who was paying attention to me on last week? What's a quick way of doing this? We know the answer immediately. Yeah, you just have to evaluate this at 3/5, and it's going to give you the answer. Mod 7, though, but we should confirm that. So here's the answer. I know that 5x minus 3 is congruent to 5x plus 8 mod 11. So I want to do this division, like restricting the coefficients to a field, because I need to divide the coefficients now. They have to be in a field. So I want to divide 10x. Oh, wow, I can do that? That's kind of cool. I don't see why I should be able to do that. But in any case, it doesn't work very well. I want to take this polynomial and divide it by this. So what's the first thing that we need to do? We need to eliminate that, correct? By multiplying this by something. Okay, so if this is 10x squared, I need to make this 10x. So how do I make 5x 10x? I'll multiply it by 2. Alternatively, you can take 10x squared and divide it by 5x, and you get 2x. Right, this is called a syzygy. Right, so I do 2x, and I multiply by this, and you get 10x squared plus 5x. Right, that's what you get by. So 2x times 5x is 10x squared. Mod 11 is 10x squared. And then you get 2x plus times 8, which is 16x. And mod 11, that's 5. Then we take the difference. So 10x squared minus 10x squared is 0, which is what we were trying to do on purpose. 4x minus 5x is minus x. Mod 11 is 10x. So that's where we get 10x here, plus 1. Now I need to eliminate that 10x. How do I do that? Well, you multiply this 5x by 2. You get 10x plus 5. Take the difference. 10x minus 10x is 0. 1 minus 5 is minus 4, which is 7 mod 11. So we can't do anything with this now. So this becomes the remainder. So this is the algorithm that we need to encode now, right? Something that we could all do, but now we need to be able to get the computer to do it, right? So here, this was the quotient, and that was the remainder there. And it allows us to write a statement like this, right? 10x squared plus 4x plus 1 is congruent to 5x plus 8 times the quotient plus the remainder, and that's true mod 11. Okay, let's do a more complicated one. This one. Okay, so now let's divide 5x cubed plus x squared plus 2x plus 6 by 3x squared plus 1. It's a little bit more tricky. Okay, so what do I multiply 3x squared by to eliminate 5x cubed? I know what it needs to be. It's 5/3 x mod 7. But what is 5/3 mod 7? Well, what's the inverse of 3 mod 7? Geez, that may be big. 3, 6, 9, which is 2. 5? 5 is the inverse of 3. 3 times 5 is 15. Mod 7 is 1. Okay, so this really is 5 times 5. Yeah, not 5/3. So what's 25 mod 7? 4. So 5/3 x is actually 4x mod 7. So if I take this and multiply by 4x, that's going to eliminate 5x cubed. But that's how I determined that. So let's see. 4x times this gives you 12x squared mod 7. That's 5x squared plus 0x. Sorry, 12x cubed, which is equivalent to 5x cubed. There's no quadratic term. It's good to write these zeros in just so they align when you're adding them. And I also have 4x plus 1. That's easy. That gives you 4x. So if you take their difference, 5 minus 5 is 0. That was deliberate. X squared minus 0x squared gives you 1x squared. 2x minus 4x squared gives you minus 2x, which is 5x mod 7. And then the 6 just comes down. Okay, so now I need to get rid of this x squared. What do I multiply 3x squared in order to eliminate x squared? 1/3. 1/3 is what mod 7? 5. So really I'm multiplying this by 5. So you get, where am I? Yeah, here. Oh, yeah. Yeah, 15x squared. That's 1x squared plus 5x plus 6. And then you take the difference and you get 5x plus 1. Can I eliminate this 5x? What do I have to multiply 3x squared by to get 5x? 5 over x. Is 1 over x a polynomial? No. So we can't use it. Right? Not now, not here, not in our number system. So we can't do anything else with this. So once the degree of this is strictly less than the degree of the thing you're trying to divide out by, that's the remainder. So here we have determined that 5x cubed plus x squared plus 2x plus 6 divided by 3x squared plus 1 has the quotient 4x plus 5 and the remainder 5x plus 1. Make sense? Okay, so this is what you could do by hand. We just need to like convert it to code. Or in our case, is it pseudocode I gave or is it real code? Pseudocode. So you give me A, you give me B. You can't divide by 0. So B is not allowed to be 0. Output, I'm going to give you a quotient and remainder such that A is equal to B times Q plus R. And the degree of R is strictly less than the degree of B, right? That just gives us some uniqueness. These conditions are required for generating uniqueness. So we're going to generate a remainder. We're going to generate a quotient. We're going to loop. And we're going to loop as long as we're able to delete like like this thing, right? We're always trying to eliminate the leading term of what's left. And how do we do that? Well, it's the leading term of R divided by the leading term of B, right? What I was doing when I said, how do I eliminate this by multiplying like this? I just took 5x cubed and I divided by 3x squared, and that gave me 5/3 x, right? So that's exactly what we're doing here for T, right? I think it's called a scissor G or something like that. Then we update Q, and then we update R, and then once that's finished, we return. Like this is if it's just identical to the algorithm that we're using for integers with a different descending condition. Here's a couple convenience methods that we defined over this division algorithm. First, we wrapped a quotient, so you can get quotients. Well, this both can't be first. What's the equivalent for second from first? Is there second from a tuple? Last? Okay, well, anyway, maybe that's not even a mistake. No, this has to be a mistake. Because they can't both be first. But okay, so here it is, like implemented in Julia for you. And have you studied this a little bit? What's weird about this? I'm not returning a polynomial. I'm returning a polynomial. I'm returning a function. Why do you think that's the case? So what did you say first? Yeah, exactly. I can't perform the division algorithm until the coefficient ring is a field. And the coefficient ring is in a field until you tell me what prime I'm working over. Yeah. But think about what we have to do with Chinese remainder theorem. We have to work with the same polynomials again and again and again with different primes. So I'm not saying you can't do it that way, but you're going to need one for each prime. I'm going to need one which is able to adapt itself to any prime. Right? So you're going to get a function back that says, I'm ready to give you answers, but you have to tell me what field I'm working in first. And then the benefit is you can keep reutilizing it, right? You can say, okay, what's the division mod 7 now? And now mod 11 and now mod 15. And it only had to do it once. Right. So you can go through these yourself. This is just showing that the algorithms are working. All right. So I'm saying I can divide P1 and P2. So let me take this out. Okay. Because this may be weird, right? So if I'm saying divide P1 by P2, I can't unpack it. It says I'm a function. And then I can do things like say, oh, okay, like your coefficient field is Z7. Oh, okay, so that's the quotient and remainder. Oh, well, okay, your division field is mod 101. Right, so that's your quotient and remainder. You can, since this division operator overloaded what this means, you can use all the Unicode stuff as usual. And same for remainder. And then here is our invariant. Okay, so here I just have, this is exactly similar to one of the hand-worked examples I gave you, but this is so you can trace your code. Right, so like if you give your division algorithm that A and that B, this is exactly the sequence of values that it should compute if you had implemented it properly. Okay, so you can use this one for debugging. Yes, sir. How do I get there's a procedure called rational reconstruction, which is this is an incredible piece of technology. Do you know who Borwein is? Do you ever heard the BBF or BBP algorithm? Borwein, Pluth, Borwein, Pluth. You know when like they ever compute like the trillionth digit of pi? This is all this Borwein's equations that he did. He was a Canadian mathematician. I worked for him and he died suddenly. Twice in my life, my supervisor died suddenly. So don't ever supervise me. But he invented a way that you can say, let me see if I can find it. We're not going to do that. It's like well beyond the scope of the course to do it, but there is a technique to recover fractions. Yeah, like Chinese remainder theorem. I'm saying, oh, the image of my fraction is this mod 7, this mod 11, this mod 13. We can recover it. Yes. Well, we can always just switch to working with the symmetric mod. So like to me, I don't really care because the numbers are equivalent, right? In my eyes. Yeah.
But then, where we are.
Yeah, when we output, we have to make sure we're outputting in a standard form, which is why we all have to agree to do symmetric mod or mod. So I'm saying symmetric mod is better, because yeah, that's the one we need in order for it to be the answer over the integers proper. But the answer to your original question is a technique called rational reconstruction, developed by Jonathan Borwein. And we're not going to go over it, but suffice to say we can. And it's kind of like a really remarkable algorithm where you just give it a number and it said, you were this fraction, and somehow it works. He was a brilliant guy. Yeah.
I'm just wondering why we need polynomial additions, GCDs, like, because with the multiplication part, all we use is the Chinese theorem, which was just the Chinese theorem for Z.
So we need to do factoring. So suffice to say, I'm going to need to do, you asked me a question that says, is modding out the coefficients the same as modding out f by g? And I said, no. So now we're going to have to talk about what it means to do f mod out by g in order to do these, like the primary purpose of this module, which is to do factoring. So in factoring, the GCD operation is going to be critical because this is how we're going to pull out factors. So because we need the GCD algorithm, we need the Euclidean algorithm, because that's what gives us GCDs. We're also going to need to generate like inverses somehow. So like, I know this doesn't, like, it's like, why are you showing me all of this stuff? It's like, there's an endpoint, and this is the endpoint. And so we'll start talking about this tomorrow, but this is the meat. This is it now. This is the super interesting part. It's a beautiful algorithm. So I'll just mention that the ring of polynomials that has coefficients from a field form a Euclidean domain. That is to say, we can get the extended Euclidean algorithm for polynomials. Right. So the same way at the beginning of class, I said we can generate these Bezout coefficients, right? That gives us a linear combination equal to the GCD. The same is true for polynomials as long as the coefficients are a field. And here's the algorithm. You don't have to study it too hard, but it's effectively just doing the same algorithm that the integer algorithm was doing, but like using the operations over the polynomial ring. Okay, so just you can study this at home, but like next time when we come together, which is tomorrow, the main part. So I want you to think about how you could factor a polynomial automatically, right? Without knowing a closed form, right? Like how do you factor a cubic, a quintic, right? What series of steps could you take to factor that for sure? And the easiest way to do it is by presuming you can factor integers. So I'm going to say you can factor integers. How can you use that to factor polynomials? And I'll answer that question first thing tomorrow, but it's a good thing to sort of think about. Okay? So see you all you guys tomorrow. And then Wednesday we have more consultation at night. Yeah. Sorry for ignoring you, chat. Oh, sharp bound means like the lowest upper bound. Like it's the closer you're, if I say you need to be at least 5, like 10 is not very sharp. 6 is sharp. Is there a particular reason we chose P3 equal 3, not 2? No. Well, I restricted I said all of our prime numbers can't have to be odd. So 2 is not a prime number in our environment. I hope you're hearing me, Mitchell. Okay, great.